Hi everyone, thanks everyone for coming to my talk. So I wanted to start with an apology because me being me, I forgot my laptop. So most of the slides here are handwritten yesterday night, and my handwriting is not the best in the world. So I apologize for the handwritten slides, and if anything is not clear, I'm happy to walk it through. The good thing is I only have about 12 slides for 45 minutes, so I'm going to be probably done fast, or let's see how it goes, but probably not over time. Okay, so I'm going to talk about gradient descent dynamics in linear diagonal network. So this is a mix. This is based on a mix of a bunch of different works. Okay. The other thing I wanted to apologize for is so I didn't give all the references in the slides. And I can, at some point, at a later point, post the slides online on my website with the proper references and with proper equations, not my handwritten equations. So I'll be speaking through some of the references, mainly because I didn't want to write down all the names and butcher it. Okay, so this is based on a bunch of different works, but the two main things I'll be talking about is one recent work joint with Matthew Evans, Scott Pesme, and Nicholas Flammarion from India, and the last two authors are from EPFL. And the early part of it, I'll start with some of the previously somewhat older results from our group from my time back in TTIC. Okay. So for all my implicit regularization talks, I used to start with a slide on giving a motivation based off of deep learning, where you talk about deep learning is essentially large networks trained with large-scale data sets. Many parts of it have changed since the last few times I've given this talk, even since the last time I gave this talk. And some have gone in very different ways, some are more of the same. So for this talk, I'll start with an alternate motivation that will just be looking at some fun optimization results involving overparameterization, sparse regression, gradient dynamics, and mirror descent, a teaser from mirror descent. Okay. So for most of the talk, we'll be sticking with this basic set of equations, this basic problem, which is just simple linear regression, but in high dimensional setting, so where number of samples is much smaller than the number of dimensions. And the most common studied case for this kind of problems is sparse regression, where you have a ground truth model which is sparse, and you're interested in recovering it. The classical, this has been studied since for many, many decades at this point. And the classical approach to it from a convex analysis, which you learn in early convex optimization, is simply L1 minimization, which is like a convex surrogate for sparsity. And today we'll be talking about how to essentially do sparse recovery without L1 minimization, or in some sense, another way to look at all these results rather than implicit regularization is to think in terms of smooth regularization, smooth implicit regularization techniques. Okay. So, so rather than start with the, okay. So our basic equation is the sparse linear regression problem, which is a convex problem, albeit ill-defined. But for the most of the talk, I'll be focusing on this reparameterized problem, where you replace W with, W is a vector in D dimension, you replace it with the product of two D-dimensional vectors, U and V. And this formulation is called linear diagonal networks because the motivation is if you write it in the form of a network diagram, it looks like a linear model with one two-layer network with linear activations and a diagonal first layer, diagonally restricted first layer. And we'll be focusing on broadly SGD dynamics or any subset of it. So we'll, in fact, first half, we'll focus on some very special cases where you update U and V according to some mini batch SGD. Here, whenever I say SGD, I specifically mean mini batch SGD and not other form of stochastic SGD, which are also interesting to analyze in this dynamics. So this has been a toy model for analysis of implicit regularization in many settings. So the work I'll talk about will talk about gradient flow, a little bit on gradient descent and stochastic gradient descent, and how they're all connected through mirror descent formulation. But there has been a lot of other people working on it. For example, there are results showing what happens if you add, instead of having mini batch stochasticity, if you add noise in the label. which kind of correlates with mini-batch stochasticity empirically. And there's results which show, there are other results which show different properties when you use large step sizes and so on. But today I'll keep it focused to some of the work we did in this space, but this space has been explored by a lot of different groups over the last few years. Okay. So here comes my handwritten slides. So again, like this formulation, as I alluded to, is essentially like a standard linear regression with U times V parameterization. And if you, some of the versions of the papers, and in fact, like sometimes it's outside of deep learning motivation, it's also easier to understand this parameterization in an alternate form, which is W plus square minus W minus square. So this kind of makes sense. W is a real valued vector. We are just writing the positive component as W plus square and the negative component as W minus square, and both can be positive. So any W can be represented in this form. And in fact, we can show that certain initialization, any gradient, any mini-batch stochastic gradient descent update on the left parameterization is exactly equivalent to mini-batch stochastic gradient descent on the right parameterization. And this is the initialization we will be going with. So this is not a standard initialization in deep learning, but you can motivate it in the limit, because the second layer in this case has a larger fan-in. So as the dimension gets larger, the standard initialization techniques push it to 0, whereas the first layer goes to something constant. And the constant is what we refer by alpha. Alpha for in the most general case will be a vector, and we'll be looking at different, how primary focus of this talk would be like how alpha influences the trajectory of gradient descent in this problem, right? And one of the basic results in this space is that if you take gradient descent, if you take the step size in this gradient descent or stochastic gradient descent update to 0, the stochastic gradient descent and the gradient descent converge to one single ODE, which is the gradient flow. And for this problem, you can show that the limit of the gradient flow will look like a minimizer of certain convex potential function subject to fitting the data. So again, to recap, this problem has many solutions. All of them will give you like, this is an ill-defined problem. And what I'm claiming is that if you start U and V with this dynamics and run a gradient flow, look into the gradient flow path and look at the limit point of the gradient flow path, you end up with a, regularization, which I'll talk about in the next slide, which is a convex regularization, and it is a regularizer which interpolates between L2 norm and L1 norm in some regimes, and it depends upon how it interpolates, depends upon the alpha parameter. And again, to recap, alpha here could be a vector.
So, Suriya, I'm a little bit confused. Sorry if you covered this and I somehow didn't understand, but like it seems to me like you're initializing at W0, right? So why does alpha matter?
So because we are doing gradient descent on U and V, so
I see, okay.
yeah, you're not doing gradient descent on W, yeah. So exactly, so we want to initialize at 0 because you can handle small initializations, but that gets even, like, yeah.
Sorry, I was just
Yeah. No, I think, in fact, like for many of the papers in the literature, including this work I have written down here, which involve like looking at this because we wanted to explicitly initialize at 0, but not kill the dynamics. And if you look at previous slides, if you initialize both U and V to 0, nothing will move, right? But if you, as long as you initialize them to one of them to be non-zero, things will move. And yeah, I think that's right. Okay. All right. And okay, so I'll talk about this minimizer. So this is a high-level idea that you get some kind of an implicit regularization here. Even though I didn't specify it in the problem, the trajectory itself like only explores some subset of the space, and the limit point of the trajectory gives you some form of implicit regularization, which is in this Q form. Now let's look at what Q looks like. So Q alpha is like an element-wise function, which has some convex function on every element, and the convex function little q looks like, it doesn't matter what is written here, it's just written there for completeness, but the main thing to look at is like, it is an interpolator between L1 norm and L2 norm. When z is inversely proportional to alpha here, alpha i's here, and when alpha i's are 0, or in other words, z is infinity, it looks like L1 norm. And the other extremes, when z is close to 0 or alphas are at infinity, it looks like L2 norm. Right? So in fact, we can show that if I started with alphas as a vector, if you, for simplicity, if you restrict alphas to be like some constant times all ones vector, as a scalar alpha goes to infinity, you will get a minimum L2 norm regularization, and as scalar alpha goes to 0, you get a minimum L1 regularization. And in fact, like, so this is not much of a restriction, because you can, a variant of this result can work for as long as it's some constant times, all the alphas are constant and going to 0 uniformly. So these results will hold, and if they are constant and going to 0 uniformly, there is some weighted L2 going on, but you still get minimum L1 norm as they are going to 0 uniformly. So now, I told you there is some algorithm where you can do U and V, and then there is some restrictions under which you can get a minimum L1 norm solution. Can you use this algorithm, use this as an algorithm for sparse recovery, right? So this was interesting from a deep learning point of view, because it kind of tells us, So this was interesting without looking at algorithmic point of views from a deep learning perspective, because it kind of tells us that just by changing this initialization scale, you can get very different dynamics. One being like a standard kernel regression, and in fact, like this is also what you would get if you just optimize with gradient descent xw minus y square without like writing it as u times b. On the other hand, you get a minimum sparse regression, which cannot be captured by any standard kernel norm. And so this is usually called the rich regime, because it cannot be captured by a kernel methods. And you get it just by changing the initialization scale to something very small to very large. So, but now if I want to think about it as from a sparse recovery point of view, the one question is, how easy is it to use this method as a sparse recovery alternative? That would depend upon, so there are two assumptions which are not, the result is not algorithmic because of two assumptions. One is like this eta going to 0, but that's not that big of an issue. Yeah.
So is it a quick way to see that it's not scale invariant? I mean, you said that somehow if alpha is smaller, then something different happens than if alpha is bigger.
Yeah.
Somehow, I guess the problem with scale invariant, if you just scale everything, that so the same problem.
Yeah, so because that kind of comes up in like, because I'm only talking about the limits. So in that limits, it doesn't matter. But it would, so this equation, oh, sorry. So this equation holds for all alphas. And you do converge to this solution when you do optimize using gradient flow in this limit. So the point at which scale comes into play is like when we convert it into an algorithm by discretizing the problem with finite gradient steps, and I'll talk about it in a few slides. So,
sorry, about the motivation.
Uh-huh.
I mean, I understand the motivation from like implicit regularization and deep learning perspective, but are you actually trying to get faster algorithms for like sparse recovery compared to like the state of the art for just solving basis pursuit? I mean,
no. So I'm not trying to recover. So it's, so I'm trying to see what it would, we don't implement this in deep learning either. So we don't implement in infinitesimal step sizes and infinitesimal things. So the motivation is still to understand deep learning or like implicit regularization in over-parameterized problems. But at a qualitative level, we also want to understand what if it's something is exponential, that's not probably what implicit regularization is doing in real deep learning. So what is actually like the algorithmic effects going on? So in that sense, I want to map it to some real world problem, which is sparse recovery, and see when we get recovery, when we not, and what is the gap in between these two. So in some sense, I am going towards algorithms for sparse recovery, but the motivation for it is to still like understand.
Okay, but then
Understand.
also as a follow-up, I mean, so here you interpolate between like the L2 minimizer and the L1.
Uh-huh.
Are there actually settings for like sparse recovery statistically where it makes sense to do something that's not L1?
Yes, so it's 2 slides from now, but I'm not going to talk about the theoretical work because we did work on it and write it up, but it doesn't improve upon existing results, so it's not written as a paper, but you can show that for sparse recovery with a little bit more sample complexity, you can use a smoother regularizer and get faster results. Mm-hmm. So okay, there is a little.
That it doesn't, okay, so I mean, it improves the optimization aspect because it's smoother.
Yes.
Even though it's a
yes.
loss on the.
But it doesn't improve the sample complexity aspect. Right. Right. And to answer your question, so you're asking why is this Q in some sense doesn't depend upon the scale of X and Y, right?
Yeah, I was just thinking that if you somehow actually scale everything up, then somehow the dynamics shouldn't really change. But or if you scale up the initialization, that the dynamics shouldn't.
It would change, right? Because how you start is initially like, sorry, I don't know how to work. So how you start will tell you how fast you move in this space, how fast you move V relative to U. I think that's what changes. So because you're not moving both these parameters at the same speed, so this V is set to 0, and you're only scaling U. So initially, U doesn't move. And how quickly V moves will depend upon the scale. Right? And that's the initial dynamics, and then it picks up. So does that make sense? Or if you want to think in terms of this parameterization, again, like, so both W plus and W minus moves, but in some sense, alpha is telling how close really to 0 you're starting. You're initially starting both W plus and W minus close to 0 versus starting something very far out. Right. Okay. So now if I want to actually use sparse recovery, so the main problem here is how small of an alpha we need. If you ask this question and actually work it out, the answer is pretty bad in the sense that you need exponentially small alpha to get epsilon close to the minimum L1 norm solution. And when I say exponentially small alpha, it's not clear how it translates algorithmically, but and in fact, like that is something you can calculate and write down, but I'm not going to talk about it. But the problem is like alpha being 0 will set it close to a saddle point, because if you remember the dynamics, V changes almost as quickly as alpha. So if you set alpha to exactly 0, nothing will move, and you're at a saddle point in the non-convex space. But by setting alpha, that's why alpha being close to 0 means you're starting very close to a saddle point, and you will not move for a long time until like V is slowly updated. So in that sense, if I actually try to discretize it, even I can write down the dynamics with small etas, and if you actually try to discretize this ODE and try to recover L1 norm, it's going to be like the solution is going to be really bad, or the algorithm is going to be really slow and bad. And especially like this exponential dependence means that like it's kind of suspicious. So so this kind of indicates that nothing we say exactly translates to deep learning, but the exponential dependence kind of shows that there might be something different going on in actual deep learning. And so we looked at what other cases we can actually do sparse recovery. And so other than alpha going to 0, so one other aspect which I didn't talk about so far, because I've been focusing on the scale of initialization. If alphas were not uniformly going to 0, then we have a different problem, which is if, let's say, alphas are behaving like this. Alpha is equal to some other constant alpha bar, and then exponentials of some, so alpha equal to alpha bar times exponential of some constant. Then as long as alpha bar, and in such a way that alpha bar is going to 0 uniformly, this is where I'm separating the components which go to 0 uniformly and the other components which are not, then you end up getting a weighted L1 norm. which may not be good for sparse recovery, depending upon how the weights are distributed across the coordinates. And in fact, like, this is something which will become relevant when we talk about finite step sizes, because when we talk about infinitesimal step sizes, it doesn't matter. I don't need to choose alpha to be very widely different. I can just set them to be some constant times all once and then run this algorithm. So this is not, if I'm just hand designing an algorithm, this is not an issue. But it will become an issue when we look at some other regimes, right? So again, now going back to sparse recovery, like we saw that this exponential dependence is kind of bad, and if you actually work out the rates, there is an exponential dependence on epsilon, which again we don't want. How to fix this? I'm not going to go into the details of the theory, but like just to give some sense of how to fix this, one is more samples. So this plot on the x-axis is the number of samples required to recover the solution. So there's no accuracy in this plot. So we set a threshold for accuracy. It's a planted sparse regression problem. Set a threshold for accuracy, let's say 1e minus 3. We want to recover to a point of 1e minus 3. We look at the minimum n such that at a given alpha you get recovery. And the dotted line up here is like the minimum, theoretically minimum sample complexity required, which is like order of S. As you can see here, if you have a very large alpha, you have to pretty much see all the coordinates, because if you have very large alpha, you're close to L2 norm, which is not going to give you any kind of sparse recovery. That means you have to see all kinds of coordinates. But you can see that as alpha gets smaller and smaller, even for reasonable alphas, you get, with a little bit extra sample complexity, you can get recovery. It's not the optimal sample complexity. There is a gap, but we can quantify this gap for this problem. Right. So the other way to also get around this is to going higher depth. So higher depth, again, I won't go too much into the details of it. Higher depth here simply means that in the two-layer case, I talked about u times b. The higher depth, I would just write it in this format. You do w plus power d minus w minus power d, and then do, again, initialize both with alpha, and then do gradient descent dynamics on w plus and w minus. So here there is a tricky thing. So the good thing is now if you calculate the implicit regularization for this problem, it's a different implicit regularization, but which again interpolates between L2 and L1 norm. But the interpolant looks much nicer if our goal was to do minimum L1 norm. So in particular, to approximate a minimum L1 norm, you only need some poly 1 by epsilon samples. Poly 1 by epsilon size of alpha. The thing and the bad thing which is not written here is like as the depth increases, like the convergence of the gradient descent for any alpha also becomes worse. So there is a trade-off you want to balance. Again, for both these cases, you can work out the exact epsilon delta and the algorithmic constants in small step size regime. And so the summary of it, which I won't go into the theoretical details, is like you can recover the existing results in sparse recovery, but not beat it, like with this algorithm, which is sometimes useful because you can. It's a much simpler algorithm. You just write it down, set the constants correctly, and run gradient SGD on it rather than do anything more complicated. Yeah.
Sorry, but to recover results in sparse recovery, you have to take. So what is depth here? Say again.
Oh, so depth is just think of this as the parameterization where instead of the original problem I started with, capital D is 2. So you write in a sparse regression problem, you write W as W plus square minus W minus square element Y squares, and then do gradient descent over W plus and W minus. So the depth here means you just write it as W plus power D and W minus power D, element Y's powers. It's just a different parameterization, that's all it.
Okay. And that's, you're using depth suggestively because this was all coming, there's some deep learning motivation.
Yeah, so essentially if you think of a depth D network where each
if I use the linear diagonal network, then implicitly I would be doing.
Yeah, so if you do, yeah, so think of it as it'll look like this, and so on, and then finally, where each layer, there's no nonlinear activation, and there are D such layers. This is 1, 2, up to D.
Okay, and is the punchline somehow that to recover the existing sparse recovery results, I have to use some, high-ish depth in order to balance this?
The exponential,
Right,
yeah.
Alpha to be
Yeah.
versus how fast do the discretized dynamics converge based on?
Right. So the discretized dynamics, I'm just trying to be as close to gradient flow as possible. So if you just like try to just mimic gradient flow, so at every point you try to approximate gradient flow with a take small and reasonable as possible. And then, yeah, so discretized dynamics, I'm not trying to do the largest step size, and I'll talk about the largest step size results in a bit. But like, yeah, try to mimic gradient flow where we know that it converges to Q alpha, and then try to compute what is, so for a given alpha, we can say that, for a given alpha, we can say what it will converge to, and then there are two components to it. One is to analyze, if I minimize Q alpha, what is the sample complexity I'll need to recover the sparse problem, right? So that is one part of the analysis. The other part of the analysis is like, for that alpha, how quickly can I get to the, like, the convergence analysis? How quickly can I get to min Q alpha?
And the point is supposed to be that, okay, my sense was, this is like a sanity check on whether implicit regularization is sort of a reasonable explanation for what's going on in
Right.
deep networks.
Yeah.
And the sanity, it passes the sanity test if you sort of wind up with like reasonable convergence rates
And reasonable.
At a value of alpha where Q alpha is also a good.
Yeah, exactly. Yeah. So it's in some sense a sanity check, but also like a way to, for us to understand what kind of initialization. You don't want initialization set to be exponentially small and something, then nothing will works in.
And also how architectural changes
Yeah.
affect
Which, yeah.
reach.
Right? Okay. So if you thought like my, I'm sorry I don't have any theorems here, but so until this point, everything can be like, everything I said can be like written down precisely as a theorem and given proper convergence rates and so on. The next thing I'm going to talk about is like what happens if, what happens in a large step size. Here again, we have like concrete theorems, but in some sense, it's the interpretation of the theorem that is more interesting, because the way we write these theorems is like, as you will see, is it can be a little bit self-referential. So in that sense, like the interpretation of it is what is more insightful. So then we started looking at what happens if you do have large step sizes. We don't try to follow gradient flow dynamics. So in this sense, we try to like actually take large step sizes and see what happens. So the motivation for this is, so there has been some recent empirical results which show that the large step size gradient descent on many standard neural networks on simple problems actually have a phenomenon called edge of stability, where you don't actually monotonically converge to in training loss, but oscillate around edge of stability point and slowly converge, but this convergence somehow leads to better solutions. And we wanted to understand this point. The problem is like even for such a simple problem, like actually analyzing large step sizes is very, very difficult. Like if you write down the dynamics, they get complicated very quickly. So like precisely tracking the dynamics becomes very complicated. So we try to look for we try to look for what ways we can phrase this problem where we can still get a good sense of what large step sizes is. Okay. So and again, to recall, like we were looking at gradient descent on U and V, and we're talking about mini-batch stochastic gradient descent. And what we can formulate is that one of the tools we can formulate is that if you take a step size, any step size such that you converge to a solution for this problem, right? And you can prove that under standard assumptions that the step size is smaller than certain constant factor of the smoothness, and constant factor of the smoothness and the boundedness of the minimum norm solution. you can actually prove this. Even though I've written that as an assumption, you can actually prove this, and we show it in the paper. And what you can characterize the limit point as some Bregman divergence, which depends upon the same Q alpha infinity. So you can characterize the limit point again as an implicit regularization problem, where it is minimizing a Bregman divergence which depends upon Q alpha infinity and W tilde 0. So W tilde 0 for now let's ignore, because it's a very small quantity, you can easily bound it away. And so it adds a little bit of an error term. But let's say you can ignore this. W tilde 0 in fact only depends upon alpha, and we are talking about small alphas anyways. And think about this Bregman divergence as approximated with Q alpha infinity of W. So what is alpha infinity? I haven't told you that. So this is an effective initialization that arises out of doing gradient descent rather than gradient flow. So when a step size goes to 0, alpha infinity is exactly alpha, so in whatever you initialize the problem with. But as you take larger step sizes or do stochastic gradient descent, you have a different effective initialization. And the problem is we cannot write this effective initialization in a closed form or even in a computable form. So the way we characterize this effective initialization is in a way that depends upon the entire trajectory itself. So this theorem by itself does not tell us much, because I can always write an implicit regularization problem which depends upon the entire trajectory as the limit point of that trajectory, and that doesn't tell us much. But that's why I said this theorem is more in how it leads us to give good interpretations rather than the theorem statement itself being useful. Okay, so.
But this path-dependent thing, and this is specifically for the stochastic, I mean, this is when
for
stochastic and you're not just following the gradient flow.
Exactly. Yes, right. And the way we actually prove it is also an interesting proof technique, which is where you can show that when step size is going to 0, the gradient flow is exactly the same as mirror descent flow on W with Q alpha as the potential. But when step size is not going to 0, it's no longer a mirror descent. But you can write it as you can write any update as a time varying mirror descent. But in this case, whenever W converges, you can also show that the limit of this time varying potential also converges. And in some sense, that converges to this potential. And even though it involves a lot of it involves many pages of proof to show that this converges, and it converges to some alpha. And whenever it converges to alpha infinity, your W infinity will also converge to the limit of that. It's a little bit tricky to show, but the high-level idea behind the proof is that, yes, it is not a real mirror descent, but it's a mirror descent with time-varying potential. And we show that the potential for this mirror, the time-varying potential over time converges whenever you're taking step sizes to be in a way that W of t itself converges. And that's where this W tilde 0 and alpha infinity come from. Right? Okay. But okay, like I said, this by itself, I think I was showing this result to Nadia, and he was heavily objecting to calling this even an implicit regularization result, because it's a self-referential implicit regularization result. But more like the way we want to think about it is like it's a tool which can help us understand some of the behaviors we observe in practice. And one of the things is like, even though it's a self-referential result, you can see that what alpha infinity becomes is alpha square, element-wise product with something which is always smaller than 1. Because you're taking exponential of minus 0, a negative number, which is always smaller than 1. So you can show that the effective effective initialization is is never larger than the original initialization. So from our original discussion, where if you wanted to do sparse recovery and we want to go towards smaller alphas, so this is a promising thing. Actually, this should be square. Okay. This is a promising thing. And so does it mean that larger step sizes always recover sparse recovery? In some sense, we can quantify it. We can show that we can call the gap between alpha square and alpha infinity, which is the initialization we started with, which determines our convergence speed, and the effective initialization we get, which determines our statistical regularizer we are getting. And we know that this gain is always greater than 0. The larger the gain, the larger the trajectory deviates from. When the gain is 0, your trajectory is exactly matching gradient flow. And the larger the gain, the larger it deviates from the gradient flow trajectory. And in some simple cases, we can analyze the gain to be like monotonic with step size and inversely scaling with batch size. So in some sense, it gives a hint on like something called the linear scaling law, which is often used in practice, where if you want to use larger batch size, typically if you also scale the step size, it works. It more or less works in practice. And this gives a hint that like the effect of the gain on step size by beta is kind of constant. So step size by b is constant, at least in this simple setting. So again, like up until this point, the gain seems to grow with eta, and then the larger the gain, the smaller the effective alpha is. So we expect that like if you increase the step size, and in fact you can see that in if you plot it and actually compute the gain, because the gain is not something we can theoretically write down, but we can compute as part of a trajectory in any problem. And we can, on the x-axis is the step size. Sorry for the mismatch notation, I just took it from the paper. So gamma and eta are the same thing. So there is a threshold for gradient descent and stochastic gradient descent when things start diverging. So the threshold is written in dotted lines. And the plots essentially show the computed gain as part of the trajectory. And you can see that like the larger the step size we take, the higher the gain we get. And especially it gets much higher closer to the edge at which things start diverging. Right? Right. So this would suggest that as we increase, and we should probably like set gamma to be at the edge of this divergence threshold, where you get the maximum gain. And in fact, this is often what we do in practice, at least for stochastic, when we do stochastic gradient descent. But at least for this problem, this procedure does not always work. So one thing we observed early on in this project is like, in fact, this figure, and in fact, the way we thought about this entire project is like, how can we explain this figure? So we again, we see that the gain actually improves, and if you put a dotted line and see what the recovery looks like, it has a very different behavior. So here on the x-axis is the step size, and the dotted lines are the same, the vertical dotted lines are the same. On the y-axis is what the loss is on a recovery problem. And if going by larger gain leads to better convergence, that seems to be true for stochastic gradient descent. It's almost like the mirror of like the scale law, where as the norm of the gain increases, the stochastic gradient descent goes down. And this is also consistent with what we see in practice, where we often set it at the threshold of like just before everything diverges. On the other hand, for gradient descent, it seems to have a very different behavior. It not only like not goes down, at some point it becomes worse, especially at the edge of stability for this problem. And this is kind of puzzling, because even for gradient descent, the scale is going up. So why is this happening? And the reason we figured out was it also, like it's not just the scale of the gain, it's also the shape of the gain. So we call it the shape, but it's essentially like how the relative coordinates within each alpha infinity go to 0. And earlier I briefly mentioned saying that if all the alphas are not going to 0 uniformly, you get a weighted L1 norm solution. And in particular, we see that like even if we set alpha to be all uniform to begin with, but do gradient descent with larger step size, the effective alpha changes. And in fact, the effective alpha changes in a way that not all alphas are going to 0 uniformly when you set the initial scale to small. And to be at this point, this can happen both with SGD and gradient descent, but it seems to be particularly a problem with gradient descent. And in particular, like we can see that if this is my effective regularization, if I put more weights on the right coordinates, so I'm trying to recover a sparse regression problem, and there are some coordinates which I want to recover, but if I put more L1 norm weight on those coordinates, I'm going to do terribly. And so that was a hint, and we actually looked into the results, and in fact, that is the case. So this is a planted sparse regression problem where all the good coordinates are in the beginning, so first 4 coordinates. And if you look at the mean over many runs or many problem instances, so the gradient descent seems to put higher weights on like the coordinates where you do have the signal. And stochastic gradient descent, because of the stochasticity, has a more muted thing. And in fact, we can, for this problem, we can calculate that at least initially, we cannot calculate throughout the trajectory, but the first few steps for gradient descent, like you can show that the gain depends upon the gradient at the initialization, and much more so than the gradients of the following steps. And for gradient at initialization for gradient descent problem is proportional to the sparse solution. And this essentially shows up as the weight in the coordinates, and that's why we see the weird behavior with gradient descent. On the other hand, for stochastic gradient descent, it still depends upon the norm of the sparse solution, but it's uniformly distributed across all coordinates. So, that in some sense is the gain. Okay, so I'll stop here because I'm running out of time. And the high-level thing is like we saw some high-level results on when we can do sparse recovery for diagonal linear networks. Again, like we use sparse recovery as a real-world problem to sanity check how different hyperparameters affect the implicit regularization. And you can already see that even though this is a very simple problem, it captures many aspects which we see in practice in deep learning, specifically the effect of initialization scale, the effect of step size, and why stochasticity is so important for many of these problems, and especially in the macroscopic step size regime. And with that, thank you for your patience. Thank you.